All right, everyone. I think it might be time to get started. Rob, Ross, if you want to bring it into the room. There we all are. Look at us. Aren't we gorgeous? This is us going out via YouTube and Zoom at the moment. So welcome to everyone who's joined us via Zoom as well. My name's Mike Flatley. I'm the CEO of the Royal Society of Victoria, if you haven't met me before. I'm now talking through a computer over there as well, which is very distracting. Thank you, gentlemen. I'm going to introduce you to Rob Gell, our president, who's going to be our MC for this evening. I was just wanting to make sure all of our technical bits and pieces were working well. So thank you, guys. It's great. I hope you enjoyed the evening. Rob.
Thank you, Mike, and welcome to everybody and those online as well. Before we begin, in a spirit of reconciliation, we acknowledge that all of us are located on the traditional country of the state's first scientists, the many different Indigenous peoples who belong to the diverse lands of what we now call Victoria. I'm coming to you tonight from the lands of the Kulin Nation. We're on Wurundjeri country here. And I invite everyone joining us tonight, either via this Zoom's webinar chat function or via the YouTube comment section, for those following the live stream, to acknowledge the traditional custodians of your own local country and join me in paying respects to the elders past, present and emerging. And we likewise extend that respect to any Indigenous Australians who have joined us in this online meeting tonight. Very warm welcome to everybody. So tonight, I'm fascinated. I had the pleasure of reading our speaker's presentation to win this award. And as a long time ago, I used to call myself a useful young geomorphologist. So I was very interested in Dr. Ashleigh Hood's work. Her presentation tonight is called Reefs, Revolutions and Redox at the Dawn of Animal Life. She's going to take us a long way back. She's the Royal Society of Victoria's winner of the 2002 Philip Law Postdoctoral Award and the first ever awarded in the new category of the Earth Sciences. Let me introduce Ashleigh a little bit more. She's an ARC DECRA Fellow and a Senior Lecturer with the School of Geography, Earth and Atmospheric Sciences at the University of Melbourne. Prior to that, she was a NASA Astrobiology Institute postdoctoral scholar at Yale University in the United States. Her research seeks to improve our understanding of Precambrian marine environments and the evolution of the early Earth's surface environments through the Neoproterozoic Era to more recent times, using multidisciplinary techniques on marine carbonates from ancient reef complexes. To do this, she integrates sedimentology, stratigraphy, and geochemistry in both the field and in her lab work. Dr. Hood's efforts have been recognised with the Royal Society of Victoria's Philip Law Postdoctoral Award in Category 3, Earth Sciences. Welcome, Ashleigh. Come up and talk to me for a minute. Yes, and congratulations. Come and stand on this side. And we'll both have to use the microphone together. Now, you better tell us a little bit about how you got into this. This is really interesting space. I'm fascinated with the sort of cross-disciplinary approach as well. But why?
I'm one of the weird people who always wanted to do geology. I really liked doing outdoor stuff and camping and rock climbing and all sorts of things. And I ended up just down this path, and I really liked fieldwork. And Malcolm Wallace, who is my PhD supervisor, did a lot of fieldwork in the Flinders Ranges, and I was sold. I said, I just want to go. So,
all right.
And here I am.
So, okay, and that's interesting. So so you got there and you found what? You started banging on hard rocks and seeing and learning a bit about Ediacron fossils and all those nice places to go and poke around. And what was there must have been something there that you went either there or when you came back that said, oh, that's worth looking at.
That's right. Yeah, so we mapped this big reef that's about the scale of the Great Barrier Reef, and except totally weird, fundamentally weird. And it was so big and amazing that I just got so excited.
Why? What was weird about
it? Sort of like
that you saw then?
About it.
That you saw then?
Just fundamentally different from anything I'd seen in the modern world, I guess.
Oh, yeah. That's interesting because this is not very modern, the Neoproterozoic. Okay, that's good. So, and you've been able to continue that on. Well, I suppose it's valuable to be able to have actually brought that to not a conclusion, but to have learned a lot.
Yep. definitely. That was just, the start of many
Yeah.
adventures all over the world.
Yeah. Ashleigh has done a remarkable amount of, she's so productive as a young scientist. It's quite remarkable. I said, nobody can do that much work in a year, but she actually seems to do it. So congratulations again. We're delighted that you're a first winner in the Earth Sciences category. We're very much looking forward to what you have to say. So welcome.
Excellent. Thank you very much. Okay, so thanks very much for having me. Thanks very much to the Royal Society as well for this really exciting award, and I'm very excited to be here. This is only the second time I've been in this building, actually, so very exciting to be standing up in front of you tonight. So my work that I'm going to be talking a bit about tonight focuses on the evolution of life as it's told in the marine geological record, so the record of sediments that form in oceans over the billions of years of Earth's history. And this work is not just my work. This is the work of many collaborators and co-authors, and I've listed some of these people here from Melbourne Uni, some students, and also from Yale University, where I was for a couple of years. So here in this picture is one of these carbonates. These are limestones and dolomites, calcium carbonate, magnesium carbonate minerals that form big reef complexes. And this is in the Kimberleys in Western Australia. And this is about 400 million years old. And it's reefs like this that tell us about the evolution of animals. And so I'm going to focus first on early reefs in Earth's history, just prior to the evolution of animals, and then some later reefs that can tell us not only about animals, but about the evolution of land plants as well. So before I get started on the research, I just wanted to put this up as a little bit of background onto sort of my motivation and what I do. So these, if anyone's seen them, NASA released some travel posters, vintage travel posters to the solar system. And this is one of the ones from Earth. And I was really captivated by this because it says, Earth, your oasis in space, where the air is free and breathing is easy. And this is a picture of Earth that we have of these green continents, these seas teeming with life, this really dynamic and beautiful planet where breathing is easy. And that's because oxygen is in our atmosphere. But that has not always been the case in Earth's history. And I look at studying ancient marine carbonates that form in ancient oceans that are no longer in the ocean. They've been moved up into the land. And here I am on some 1.9 billion year old stromatolites in northern Canada. And I use these ancient reefs to tell us about how weird and wonderful the Earth was back in the day. So to do that, I started with fieldwork, and I'm a big fan of fieldwork. I've not been able to do any since the pandemic, but a lot of my work is based in Central Australia in the Flinders Ranges, which I'll show you a bit about today, where we've been, stalked by emus. We've been up in Canada, stalked by bears, Namibia, surrounded by elephants, and in America, surrounded by Americans, I guess. And each of these places has these really old geological records that we can use to understand its history. And then I take these rocks, we measure them, we find out what they're about, we take them back to the lab, and we dress up in these amazing outfits, and we can do chemistry on the rocks and tell us about what the seawater was like back in the day that these weird reefs were growing. And so I do microscope work. I cut thin sections and look at the sediments themselves. I do isotope geochemistry, and also at the University of Melbourne, we do a lot of laser ablation work, which is always very fun as a scientist to zap things with a laser. Okay, so that's how we do it. But why am I interested in this early part of Earth's history? Well, this diagram, which I've stolen from Wikipedia, I think, really nicely shows what we understand about the history of life on Earth, basically, our understanding of the evolution of life as it's preserved in the geological record. And so in modern parts of Earth's history, millions of years ago even, we have a pretty good understanding of what's going on. We know what's happening in the oceans, we know what's happening on the continents, we know about climate. We know a lot about the recent past, but as we go back past the dinosaurs up here somewhere and back to the very edge of animal life in the Precambrian boundary around 540 or so million years ago, and we go into the Precambrian, our knowledge really spirals out of control. And you can see this nicely on this diagram. We don't know what's really happening. We think there's some stuff in the oceans. We don't know if there was even land. There was land, but It's a pretty unknown part of Earth's history. And this is why I like working in this area. It's a little bit like the Wild West. There's a lot of wacky theories out there, of which I've contributed some, I'm sure. And so this early Earth, very, very early in Earth's history, back maybe 3 or 3.5 billion years ago in the Archean, this is maybe an artist's impression of what the Earth might have looked like. So very different from the Earth we know today, devoid of oxygen. The atmosphere was instead composed of methane. It was perhaps the skies were orange, like Saturn's moon, Titan. There might have been organic hazes that drifted and dropped into the oceans in the atmosphere. Super greenhouse. The oceans themselves are really reducing. The whole planet's surface was reducing. So we have things like dissolved iron, which would have given the oceans probably a green color. So very different Earth's landscape. And recently, we think actually that the origin of life was not necessarily in deep sea vents, but in these sort of shallow or near-shore hydrothermal systems like hot springs, where possibly the origin of life and early life preserved in the geological record possibly comes from these environments. So the early Earth was a fundamentally weird place, and basically the process of oxygenating the atmosphere, oxygenating the Earth, has been the most important process in Earth's history in changing this planet into our oasis in space, the planet that we know today. Okay, and so this is just a diagram on the left here, which shows how, with the traditional view of how the Earth gained its oxygen over billions of years. So here on the x-axis, we go from 4 billion to 0, so very long timescale represented here. And on this axis, we have atmospheric oxygen as a percentage of modern day levels of oxygen. So 100% is modern day, so 21% of the atmosphere. So we know that in that early part of Earth's history that I just showed, that we had vanishingly low amounts of oxygen, almost none. But during this time, cyanobacteria evolved and they pumped out oxygen. And we had this great oxidation event. And we have pretty good chemical evidence for this event, around about 2.4 billion. This middle part of Earth's history, which is often called the boring billion, which is pretty unfair, maybe. This period of time, it has very uncertain oxygen levels, but probably also very low, probably in the order of about 0.1% of present levels. And then there's a second event here, the Neoproterozoic oxygenation event, which was associated with the rise of animals. And so these oxygen events are intimately associated with the evolution of life. And I'm interested in understanding in more complexity than this two-step model, how this happened. And reefs are sort of a perfect place to do this because they are hotspots of biodiversity. And if anywhere is going to host what things they can tell us about oxygen and things they can tell us about life, it's reef complexes. So before, I guess just as a little bit of background as well on the history of life as it relates to this oxygen history before I get into my own work, I just wanted to put this up. So this, again, at the top here, there's a graph of all of time, 4 billion to present at the right, and oxygen concentration up here on this axis. And this is just a more updated sort of model of this two-step history with these two big oxygenation events. So in the Archean, I mentioned, is the evolution of bacteria that photosynthesize. And these create, down here on the bottom left, these create structures called stromatolites. And we can recognize these in the geological record back to about 3.4 billion years old. After this great oxidation event, there's a big jump in oxygen, still to very low levels, but it's permanently oxygenated for the first time. We start to see the evolution of eukaryotes, and these are more complex celled organisms. So these have a nucleus in the cell. And this is an example of the type of eukaryote that characterizes that early part of the record, this Proterozoic boring billion. And it's an organic walled microfossil, and you can see a little ornamentation on it. And these are pretty standard through the geological record until we get up to the Neoproterozoic, and that's where they start to diversify. So in the start of the Neoproterozoic, so we're talking about 1 billion years old now, we start to see the evolution of green algae. And this is one of many multicellular eukaryotes, sorry. So these are complex and multicellular now. And this is an example that they've recently found in China that you can see. So it's macroscopic for the first time, as opposed to these microscopic earlier fossils. But then right in smack bang in the middle of things getting going, these two blue bars represent a massive glaciation that really throws things around a bit. So there's two of these, the Sturtian and Marinoan, and these are thought to be, they're called snowball Earth. They're thought to be a time where the whole Earth froze over, almost entirely covered in ice. And you can see that would have had a pretty severe effect on animal evolution. So things got delayed for about 50 million years or so. And these ice ages are thought to have gone for about 55 million and 5 million years each. So very long period of time. That's the same length of time as the dinosaurs till today. So just that's a very severe disruption to the evolution of life. But right after these big glaciations, so right after we get the first evolution of animals. So we see the Ediacaran fauna, and these are what Rob was talking about before. These are these beautifully preserved, unusual, soft-bodied animals that exist in just prior to the Cambrian boundary, the explosion of animals. And these are very weird creatures that have a lot of, there's a lot of evidence that suggests that some of them are related to certain groups of animals, but really don't know the affinity of a lot of these things. Just after that time, we also get the first biomineralizers. And so these are reef-building organisms that build shells. These are the first creatures, Cloudina, that start to build shells. And there's reefs in Namibia that have these beautiful creatures in them. Right after that, we get the traditional Cambrian explosion of life. So this is where the Burgess Shale, this is where many of these weird and wacky animals that you see in science documentaries are documented. So Anomalocaris is a classic strange creature that eats trilobites. So this all happens around about this period of time at the end of the Neoproterozoic, associated with this oxygenation event. And of course, much later in geological history, we get the evolution of trees. And so land plants and forests don't actually arrive and green the continents maybe up until about 450 million years. So quite significantly later than animals evolve. Okay, so we're sticking with this all of time, along with the evolution of life being quite different as we go through time. The oceans, which have hosted that evolution of life, basically up until land plants evolved very late in the piece, they have changed significantly through time too. And this is what my research is mainly focused on. So in the Archean, again, this early part of Earth's history where we had the green oceans full of iron, these are called ferruginous. And that's a term that means there's no oxygen, but there's a lot of iron dissolved in the oceans. Probably very, very small amounts of the oceans were oxidized. And here is our reef, for an example, which would be growing in totally oxygen poor conditions. The middle part of Earth's history, when we've gone through the first oxygenation event, is a mix of, it's a variable redox state. So redox means the sort of state of how reducing or oxidizing it is. And so we have euxenic conditions, and these are sulfur-rich, low oxygen, iron-rich, low oxygen, and some of the upper water, so probably in our shallow parts of our reef complexes, we might have some oxygen. And then in the Phanerozoic, so this is our modern era, the era of modern life, the oceans of today, for example, we have a lot more oxygen. So this is a kind of a very simplified view of what's happened through time. And life has evolved through all three of these conditions, basically. Now, of course, that in the diagram there, I just showed you these little reefs that exist in these oceans. The reefs themselves host life in a variety of different ways as we go through, and it's associated with these ocean conditions. Early in Earth's history, our reefs are very strange. They are mainly composed of crystal fans. So these are crystals that form out of seawater, kind of like salt does. Big fans of these on the bottom of the seabed in shallow seawater. Lots of microbes creating things like these stromatolites. And really, stromatolites and crystals dominate most of reefs all the way through the Proterozoic. So all the way through this middle part of Earth's history, most of our reefs are made entirely of stromatolites, plus or minus these weird crystals, which possibly associated with really alkaline oceans back in the early days. And then it's not until, again, this Neoproterozoic oxygenation event that we start to get reef frameworks that look like modern coral reefs, so modern reefs like the Great Barrier Reef. So they have a more complicated framework, in this case, probably largely still microbial, but much more complicated than just stromatolites. they have these crystals that form as you pump seawater through the reef. And these are called marine cements. And I use these to look at the chemistry of reefs at different depths because they precipitate essentially from seawater. And so they directly record the chemistry of the seawater. And so this Neoproterozoic sort of big change, fundamental change in reefs is possibly related to oxygenation, but it's also possibly related to the complexity of life that's developing during this time. And in fact, you know, I say the history of reefs, but actually up until some of the work that we did on the Neoproterozoic reefs, there was really only one example of a reef complex from the Neoproterozoic. And this is 500 million years versus history. This is the same time from the Cambrian till now. So this is a very long period of time. And this reef here in northern Canada was the only one that was really documented. So this one's about 800 million years old. It's in the Little Dal area of the Mackenzie Mountains, very hard to get to. I was going to head there on a helicopter in 2020 before the pandemic, but alas. And these are Pinnacle Reefs, and they have these complicated frameworks. Don't worry too much about the detail here, but basically the little dark brown bits are microbes that are able to calcify themselves. So they're like an intermediate step, I guess, between a complex biomineralizer, like a thing that makes its shell, and a microbe that's just hanging out and ambiently existing in a rock. So more complicated sort of modern style frameworks, but still they look big here, but they're still pretty small reefs compared to something like the Great Barrier Reef today. Okay, so this is where we are now. We're younger than those 800 million year reefs. We're in the Cryogenian, which is in the middle of those two big ice ages that I talked about. There's a big tropical period of time around about 650 million. And during this time, we have these big reefs develop in the Flinders Ranges in South Australia. And so here we are standing, or we're flying actually over one of these big glaciations, and all the way from the bottom left up to the top right of the screen, that's about 100 million years of history recorded in sediments. And they're beautifully exposed. There's lots of really spiky bushes up there, but aside from that, beautifully exposed and perfectly preserved reefs in this period of time. So that's what it looks like today. What about back in the day? So around about 715, this graph this sort of diagram is showing. This is the Earth as reconstructed by geologists. So you can determine yourselves how trustworthy you think it is. This is during the breakup of one of these big supercontinents. So like Gondwana, but this one is called Rodinia, and it's starting to break up. It's starting to rift apart here. This is where Australia is situated. This is where South Australia is during this period of time. So we're sitting in tropical latitudes. And all through the northern Flinders Ranges, so we're talking about now on the top left here, about a day's drive north of Adelaide, near Karula, for anyone that's been up there, this is Karula. You have a series of big platform reef complexes, and you can see the scale in the bottom right here, it's 10 kilometres. And these reefs, there's a series of them, Karula Unaminta, there's one way up north of Mount Fitton. Each of these is maybe up to 10 kilometres long. So these are preserved in cross-section. These are preserved in the mountains. They're obviously no longer in the water. And each of these preserves this beautiful record of very unusual reef systems. And I'm going to show you a little bit about these reefs themselves. So I'm going to focus in on the two that we've done the most work on. And so that's the Unaminta Reef here. And Karula Reef, and these are situated around Karula itself. And so Karula, the property, is actually owned by the kids of Reg Sprigg, and he was did a lot of geological work in the area. He's a bit of a famous guy, and he discovered the Ediacron fossils. If I got that right in my head, hopefully. So a very prospective area for good geology. Here we are. This is the stratigraphy here. These are the layers of the rocks. So this is the early glaciation, the tropical bit in between, and the second glaciation. And you can see again the scale of these things. These are tens of kilometres long. They go from the shallow area here down the bottom all the way into the deep ocean as you follow these units around here. And I'm going to show you a little bit about what they look like. But I guess first, for context, this is an example of a modern barrier reef like you'd see in the Great Barrier Reef. And so just as we're going to go through our ancient reef, I thought I'd just put this up here to show you what our modern reefs look like. So very shallow sort of back reef platform area. We have tidal like beaches and stuff at the land side. Our margin of the reef is practically out of the water surface. If anyone's ever been snorkeling in a reef, you could find yourself, sucked through basically and almost hit a whole bunch of corals. So everything's happening in this upper part of the reef, and you can see here the scale. So the reef itself only goes to about 150 meters water depth before you can no longer support corals and other things to grow. And down here, so this is called the reef slope. So modern seawater, of course, has abundant oxygen. So there's no problem with things living in this upper water column. There's no problem with them living anywhere in the water column, but they're limited by light. So in contrast, this is a version of these Balkanuna reefs, these 650 million-year-old reefs. So again, we've flipped the picture around here, but we have tidal settings. These are red beds, really unusual hematite-rich or ochre-rich red beds. We have a shallow platform which extends for kilometers and kilometers out to sea, which is essentially the whole way through only a couple of meters water depth, really, only up to maybe 15 meters water depth. Our framework here is made up of two different frameworks. So instead of corals, we have stromatolites in the top part, which is pretty common. And the bottom part, we have these really strange creatures, which we don't really know what they are. And we've just called the non-stromatolitic framework. But you can see here, this is like 90 degrees. This is basically a cliff that exists in the ocean. And modern reefs don't have this sort of geometry. They tend to be much more gentle slopes. Likewise, you can see the scale here. This is about 1 kilometer. And this cliff itself is probably up to about 800 meters at most. So things are living down in the dark water, and they're living at depth, and they're not concentrated at the surface. It's a very sort of different perspective to modern reefs. Because they're so steep, often the reef will oversteepen and stuff will fall off, and it gets thrown out into the basin in these massive debris flows. And you can get blocks about 1 kilometer big that have just tumbled off the reef face and fallen into the shales below. So the reef itself is composed entirely of dolomite, which is a magnesium carbonate mineral. And so this is different from modern reefs, which are composed of calcite, so calcium carbonate. But pretty common in the Precambrian. So I'm going to go through what this looked like. So these are our red beds. You can see things like this in maybe Qatar or these kind of salt flats around that area, except these ones are full of hematite. We get teepees, we get ripped up bits, we get mud cracks, all sorts of things that indicate that you are exposing this to the tide and regularly exposing it to the atmosphere. As we go further out into the platform, so very shallow still, we get these unusual things called sheet cavities. And these are big cracks that appear, bedding parallel cracks that appear in the dolomites. And they're full of these crystals, these marine cements that precipitate from seawater, and we can use these to tell us about the seawater chemistry. The rock itself is often made of these little grains called ooids, which are essentially like little carbonate pearls that float around in shallow seas in places like Bahamas. And so tropical, sort of very shallow seawater. And so I imagine it would have been a very nice place, aside from possibly the lack of oxygen back in the day. So that's our shallow platform, and now the reef margin itself. This is a picture of one variety of stromatolite. So this is a branching form, a pretty small branching form that you get. And the reef margin itself is composed of a huge abundance of different types of these stromatolites. So these are all laminated microbial structures of different sorts. The upper ones probably are photosynthetic. They usually point upwards, which tells us they're growing towards the light. And the slope here we can calculate using the growth surfaces of these stromatolites, and that's actually work I did during my honours. And so these go from about 45 degrees slopes down to about 90 degrees slopes as you get a little bit deeper. Around about 150 meters water depth, or ancient water depth, this is probably in an area where you're not getting much light. So these stromatolites down here, these microbial ones, are probably not photosynthetic. They're probably using some sort of other energy source, of which we don't really know what they do, what they're living on. Now, underneath the stromatolites, so under 150 meters water depth, are a number of different, what we've called non-stromatolitic frameworks, so weird microbial frameworks. This is an example of one. I haven't got a scale, but this is about 1 centimetre across. The little pink bits here, these kind of branching pink structures, are little calcifying microbes. So these are these microbes that can build their little calcium kind of sheaths around them. And you can see here they grow and they branch outwards as they go upwards. This structure here is called a Neptunian dike, and it's basically a crack that forms in the reef when it gets too steep, and the crack fills with these cements. So again, we can use these to reconstruct the chemistry of the seawater. This is a common framework in some of the reefs, but in other reefs you get another unusual framework, which again, here's a centimetre scale. So these are macroscopic. They look like bubbles sort of in our crop, but actually when you look at them in thin section, this is a thin section view under the microscope, these are really unusual kind of complex looking structures. And originally, we were trying to figure out what these things were. So you can see again the scale, this is 0.5 centimetre. These things are macroscopic, they're not microscopic. They superficially resemble actually sponges, which are animals, of course, they're the lowest sort of, the most primitive animals, but sponges, porifera, have filter feeding networks. They have little pores that they can suck water in and out of to use to feed. And these things don't have a pore system. So we don't think they're sponges. They certainly do look like some primitive sponges. They possibly are some unusual complex microbial community that's sort of organized to form these things. We don't really know, to be honest. And if anyone has any ideas, I'm happy to hear them. This particular one is a lobate type, and we see this quite commonly. It's got these little cusp-like projections and little sort of chamber walls, we call them. We call them chambered structures, essentially. This is another type, a dendritic. This is a dendritic type, and you can see it's got more polygonal chambers. So, and we see this in Australia, and we also see this in Namibia as well. And we've recently also seen them in Canada, so all over the place. And you can see here this one branches. So unusual chambered structures, whatever they are, whether they're complicated microbes or some version of a primitive eukaryote, I don't know. They're living in the deep and they're living in the dark. And they grow over these big debris, these big chunks of reef that fall off, and they extend out into the basin below. So that's just what these look like, the slope facies. These little orange or yellow blocks here, you can sort of trace them back over the hills. One big debris train of a reef collapse event. So maybe like an earthquake would cause this, and a whole section of the reef collapses and just goes all the way down, way into the deep sea. And here, this is the reef up here for context as well. Okay, so I mentioned sort of as we went through those different areas that we found these cements, these marine cements in each part of the reef, in the shallow area and in the deep area. And these cements, it turns out, are really unusual compared to modern day marine cements that you'd find in reefs. So in modern days, these are usually composed of aragonite or calcite, calcium carbonates, but these ones are composed of dolomite. And part of my PhD work was trying to figure out how these had formed. And it turns out that they actually precipitated as dolomite from seawater, which is really unusual. Today, you can't really do that from seawater. You need some massive difference in the chemistry of seawater to be able to precipitate dolomite directly. The only places today you might get dolomite are places like the Coorong, South Australia, really kind of stinky nearshore lagoons that are probably not the most exciting places of all time. Not that I'm saying the Coorong's bad. Coorong's a great place. You should all go. But these, so these have crystal properties, and these have luminescence properties here on the left that tell us that they precipitated as dolomite from seawater. And this is really great news for doing chemistry, because dolomite turns out to be a much more stable mineral over geological time. And so because we can see this beautiful zonation pattern in the cements, it tells us that these are recording essentially little variations in the chemistry of seawater as they grow over probably maybe hundreds of years. And because we still see this beautiful zonation, it tells us that we still preserve that chemistry really beautifully in the reef cements. And so this is just a bit of a cartoon about what they can tell us about what these reefs were like. So just up here on the right, so each of these bars represents the thickness of the bar represents relatively how much abundance each element is in each different depth of the reef. So around about 0 meters water depth, and maybe at 10 meters water depth, and down to about, say, 200 or 300 meters water depth. And really the most important, the rest of these tell their own story, but the most important is actually iron. So iron is found in huge abundance, even in shallow waters. So even in only 10 meters water depth, you've got a huge amount of reduced iron in your seawater. And so we can tell that actually this means that the seawater was anoxic, it was devoid of oxygen. Because if you had any oxygen in the seawater, it would bond with the iron and it would drop out as an iron oxide. The only place that we see that is in those red beds in the nearshore. That red color from the ochre is basically where iron is forming with the oxygen and precipitating iron oxides. But the rest of the reef, even with waves and everything in this shallow part of the platform, is totally devoid of oxygen. And so these creatures, whatever they are that live in the deep part of the reef, appear to don't need any sunlight and they don't need any oxygen to live. So very sort of unusual situation. And this probably is characteristic, it turns out from the later research we've done, of Neoproterozoic reefs in general. These early reefs tend to be anoxic at depth, and they have these complicated frameworks in really deep water. So here is here's again time from about 1 billion up to the Cambrian explosion of animals around 500 million or so. And in white here are this is the reef that was that I showed at the start, 800 million year old, the one that was documented. There's some right at the very end of the Precambrian, about a couple of million years before the end of the Precambrian. But all these ones in blue are the ones that we've now documented and looked at and added to this record. So there's much more complexity, it turns out, than just one reef from 500 million years of Earth's history. There's so much more to do. Some of these are in Canada, some are in Africa, Australia, they're all over the place, it turns out. Recently, they've also been documented from China. So, and so these are complicated reefs that grow in anoxic seawater. And then, of course, when we get into the Cambrian, we start to see our more sort of modern looking reefs. So we have microbial frameworks, we have corals, we have sponges. And this is an example from Ellen's work, who's here in the audience. And she's looking at Cambrian reefs in the Flinders Ranges, which turn out to be really, really beautiful as well. And this is an example of one of the early corals from some of the blocks that we found in the Flinders Ranges. So, so a really sort of rich history of reefs, and a more complex understanding, I think, that our work has looked at than perhaps just this one data point, basically. Okay, so just the last bit of the talk, we're going to shift gears. So I've talked about one reef and what it can tell us about one sort of ocean basin. And now I'm going to show you putting together all these reefs that we've looked at from about 1 billion years to today, and what the marine cements can tell us about the chemistry of seawater through time. So how can we add complexity to that oxygen history that I showed right at the start? And so it turns out to be a story that's more fundamentally based on the evolution of plants than the evolution of animals. And so here's some early land plants, a nice artist's impression of some early land plants. And I'm going to do this using the rare earth elements. Okay, so before I talk a little bit about the rare earth elements, so these are examples of the types of rocks that we use to construct this. So these are all from reefs, like I showed. There's marine cements shown here. Some of these pictures here are called cathode luminescence images. They essentially are, the luminescence is caused by the amount of iron and manganese in the carbonate. So marine cements were the most sort of the best things we use to reconstruct this history because they precipitate directly from seawater. We also use microbialites where we could find them, which have also been demonstrated to be good, reliable indicators of seawater. And we even use some things like brachiopods. And so our work looked at 16 different formations using laser ablation. And then also we compiled a list of literature data, of previously available data, and modern seawater data to base our study on. So the proxy that we look at, the proxy means the chemical, I guess, proxy of the marine cement that can tell us about these ancient ocean conditions. So a redox proxy is a thing that can tell you about ancient oxygen levels. we use the rare earth elements. So these are a series of lanthanides. They go from, at the bottom here, from lanthanum all the way up to lutetium, so from light to heavy. And they have very chemically similar behavior. And when you normalize these, so I don't want you to worry too much about the details here, but essentially when you normalize these to the normal composition of the crust of the surface of the Earth, you can get these profiles, and each profile shape can, with its little anomalies that exist, can tell you about the fluid composition. So modern seawater, for example, has this characteristic shape with this spike, negative spike here with the cerium anomaly, and this other positive spike up here. And they've been really well studied in modern systems. And so we can use them to understand the fluid chemistry of the past, the oceans of the past. The one thing I want you to focus on now is this cerium anomaly. So cerium is redox sensitive. So it's sensitive to oxygen, whereas the other rare earth elements aren't really as sensitive, or at least the surrounding rare earth elements. And so when you have oxygen in your fluid, in modern day seawater, you have oxygen dissolved in the seawater, you remove the cerium, you essentially deplete all the cerium, it's taken out and sorbed onto these oxides as they precipitate. And so you get this big negative spike in these profiles. And really what this means, it gives you a, you can do a calculation and get a number from this. If you have no negative spike, you just have a flat line, you get a number of 1. So it means that there's no difference between cerium and the surrounding rare earth elements. If you have this big negative spike, you get a number that's less than 1, and that indicates there's oxygen present. So essentially we're looking at no oxygen is around 1, and anything less than that shows you that there's oxygen. And so this is what we've used with all of our lasering of all these marine cements. This number is what we use to reconstruct the oxygenation history. Okay, and this is what we came up with. So it's a bit complicated, but we'll just go through it. So down the bottom, this axis is time. So going from about 800 on the left to today on the right. And this axis here is our cerium anomaly. So the gray line in the middle is 1. So this means essentially no oxygen or low oxygen. And this orange line represents what we see in modern day carbonates. And so it's around about 0.6. So anything above that line suggests modern oxygen levels, seawater with modern oxygen levels. And so sort of as we go up, we're getting more oxygenated. The blue dots are every laser point that we analysed, and the red is the average, and the grey are the literature values, and again, the red is the average. And so firstly, you can see when you look at this data that the early part of Earth's history here, this 800 million year old rocks and our reefs at 650 million, the one I showed you earlier, these are essentially at 1. They're showing no oxygen present. These are telling us that this particular period of time was very anoxic. And again, these 2 grey bars are these glaciations where we have the snowball Earth. There's a big jump, and subsequently we've actually added data into this. So it looks a bit sparse here, but there is data now that shows this is a significant trend. We have this big jump in oxygen up to sort of modern-like levels, just briefly. And this happens around the Ediacaran, and this happens exactly when these weird soft-bodied Ediacaran organisms evolve. But strangely, by the time we get to the Cambrian explosion, where we see animals everywhere, we drop back down again to low oxygen levels. And most of the Paleozoic, or this era of kind of old life, I guess it's not an era of old life, a time of sort of very early life, early animal life, we see low oxygen levels. So not quite as anoxic as before, but still not looking particularly good. And actually this turns out to be not surprising when you look at the geological record, because we see a lot of rocks from this time, a lot of black shales, organic rich shales, which suggests that at least the deep ocean is probably still fairly devoid of oxygen. And it's not until we get to the Devonian here, when we have the evolution of plants, that we really kick ourselves above this orange line and we start to get into a more modern oxygenated world. So I'm just going to show you some pictures now as we sort of step through this time, focusing first on this transient oxygenation event in the Ediacaran. So here's an image. This is one of Peter Trussler's paintings. These are these Ediacaran fauna, these soft-bodied frondose organisms that lived in these. This is an example from the Avalon assemblage about 580 million years ago. These ones are actually in the deep sea. And so probably the oxygenation event we see at this time, even though it was transient, actually pumped oxygen all the way into parts of the deep ocean. And by deep, I mean several hundred meters water depth. And these organisms actually sort of went extinct by the time we got to the Cambrian explosion. And there's been arguments about what caused their extinction. It's possible that it is related to this change in oxygen conditions. It's also possible that it's related to the fact that these terrifying predators evolved. But I'll leave that to paleontologists to look at in more detail. So these are some of the creatures we see in this Cambrian explosion, which happens, in this period of time where we're seeing not much oxygen. So it's not, this is interesting because it's showing us a different story than the one we saw before. So it's not that, animals necessarily, they need oxygen to breathe, obviously, and to live, but they don't appear to need our modern levels of oxygen to be able to survive. Probably in this period of time, our shallow water was oxygenated, but much of the deep ocean wasn't. Okay, so what about this big jump then? This seems to be the most fundamental change in our oxygen history. And so this is actually associated with the rise of land plants. And early land plants, like these ones here, Cooksonia and Baragwanathia, actually were these small, sort of like beautiful, exquisite plants, but small, and they were restricted to places like coastal swamps. So it's possible that these early land plants didn't play a huge role in changing the biosphere of the continents. But just for some sort of trivia here, Cooksonia is named after Isabel Cookson, who was a paleobotanist at Melbourne Uni. And Baragwanathia, which is one of the earliest fossils, earliest land plant fossils found, that is vascular, so has a system to transport water. That was named after William Baragwanath, who was a geologist here as well. So Victoria has a really rich history of these really early land plants. But unfortunately, it seems like these early ones kind of weren't big enough to cause this big change in oxygen. This is leading up. This is about 50 million years before we see this big jump. This is what these early ecosystems might have looked like. So there's 3 different artists' impressions. Again, Cooksonia here, probably forming in these sort of coastal swamps. Here's a nicer, sort of more modern one where we see also these giant 8-meter high prototaxites, which might have been fungus, we think, sort of strange looking landscape. So these are the ones that evolved in the Silurian or early Devonian. But when we see the big change in our records, so again, these numbers showing anoxic sort of numbers around about 1, our first values of cerium, where we see lower numbers suggesting oxygenation, occur right in the time in plant history where we get big trees start to evolve. We see big forests growing. Our little kind of Cooksonia and our little plants that had little shallow root system and kind of existed on the fringes of the water, they'd only just kind of climbed out of the water essentially. It's not until this time, the Franian in the late Devonian, around 380 million years ago, that we start to see these big trees evolve. They have root systems for the first time that can form soils for the first time. And we think it's this time that really shows a big change in oxygen, a big change in the biosphere in general. So in the mid-Devonian, when these first trees we see, these Archaeopteris or like ancient fern, I think it is, these have evidence for some of the earliest root systems. And some of these have been recently discovered in New York State. We see these traces of these root systems of these ancient trees. Really beautiful, beautiful forests. And these sort of paved the way for then in the late Devonian for big forests to become widespread. And here, these late Devonian forests, where we start to first see this oxygen trend, we have large trees become quite common. They have much more well-developed root systems. They're much more able to form soils. In fact, this is when we form the oldest coals, this period of time. These represent essentially a huge new source of oxygen. So they not only do they photosynthesize better, more efficiently to create the oxygen in the atmosphere, they also are made of organic matter like lignin, more resistant to breakdown. And so one of the ways you can sort of maintain oxygen in the atmosphere is by taking organic matter and all that reducing material and burying it. And for the first time, this more resistant organic matter allows you to do that, to bury all of this organic matter reductants and keep that oxygen in the atmosphere. And we think it's fundamentally trees that are the architects of our modern beautiful world that we see today. Which is, I guess, a bit of a surprise for us because everyone had focused on animals being sort of this key aspect of this oxygen history, but it turns out plants play a much larger role. But you can see the effect that this has had on animal communities as well. So this is a diagram by Fanatau 2020, and they show on the left the number of species through time. So from the Cambrian explosion up until the Triassic, about 260 million years ago. And I want you to focus, I guess, on this picture here in green. And these are animals that evolved in the Cambrian. So in this early part, in these low oxygen oceans. And you can see that in these low oxygen worlds, these make up a large diverse part of the sort of extant species or species in total. But as we go into these earliest land plants and then into the evolution of forests in the Devonian, all of these animals become extinct. And actually, Cambrian faunas are totally extinct basically by the end of the Devonian. And I think this really nicely shows that these animals perhaps were adapted to a different world. The pre-Devonian world was a fundamentally different world after oxygenation, before oxygenation, then afterwards. And you can see this as well in the type of animals that we have. So in the Silurian earlier on, we have these kind of weird and wacky creatures that live in the sea. They might look slightly terrifying, like this guy here, and Eurypterids and stuff like this. But perhaps they were just kind of all hanging out, having fun. They were eating each other and stuff like that was happening. But they weren't as absolutely terrifying as the things that came after the Devonian. So the Devonian, the age of fishes, this is when we see these plachioderms. These can get up to like 7 meters long, these giant armored fish. We see sharks evolve during this time. Amphibians for the first time crawl out of the oceans and go onto land and breathe the oxygen. And so we really think that this change in oxygen has really promoted not only the change in plants, but also has had a huge impact on animal life as well. Okay, so just to summarize, I've got a summary and just a couple of thoughts. So our first part of the talk looked at these Precambrian reefs, which show complex frameworks in these anoxic waters, these low oxygen waters. So it's, there's a lot of stuff going on prior to the evolution of animals. And it turns out these reef complexes are great places to look for this, to see this kind of diversity and complexity. But it was the establishment of land plants in the Paleozoic around the end of the Devonian that really we think was essential to turn us from this previous anoxic world into our modern, beautiful planet that we know today. And so you might be thinking, that's really nice that we know 400 million years ago that the oxygen came to the atmosphere. That's really cool, but whatever. But I think this has a really fundamental role to play in some of the most fundamental parts of science. And so I'm really excited at the moment. We're in this sort of part of the search for life in the universe. Are we the only things out there? And it turns out that this work can play a role in that search for life elsewhere. So here, this year, the James Webb Space Telescope has been launched by NASA and others, and one of its missions, it's been releasing all these beautiful photos of galaxies that some of you might have seen, but one of its missions is actually to look at the atmosphere of planets that formed outside our solar system. So these are exoplanets, and there's more than 4,000 of these that have been found. There's stacks of these planets out there. And this telescope is going to fundamentally be able to check out what gases are in the atmosphere. And the idea is, can it search for life using the composition of the atmosphere? So you'd imagine something like oxygen, which is created by life, is a very good example of a type of atmosphere that might be prospective for life elsewhere. And so, I think this is just starting to come online now. This is really exciting. Of course, we also have the Mars rovers out there, and they are looking for magnesium carbonates, like the sort of carbonates that we have in our reefs. So I think there's fundamental ties here. And so, coming back to the end then, this beautiful planet that we have today, our oasis in space, this Webb telescope is up there looking for life elsewhere. And this in the 90s was what Carl Sagan said about if you saw our planet as like from a telescope from a distance. He said there's evidence of abundant gaseous oxygen and atmospheric methane in extreme thermodynamic disequilibrium. And together these are strongly suggestive of life on Earth. And I think this is amazing that we can, potentially find this in other planets. But I think our work has shown that potentially this beautiful oasis in space where breathing is easy is only something that's about 400 million years old. And this idea of finding perhaps oxygen and methane, which shouldn't exist together without life producing them, is something that we maybe need to broaden our horizon. So life might be a very different state in different planets. You know, in different times of Earth's history, there's been very, very different situation where we have a certain type of life and a certain type of atmosphere. And so, yeah, I think this is really exciting. This is a new direction that we can push some of this research. And also, you know, it makes us appreciate our oasis in space at the moment. And, you know, our planet will obviously be fine through climate change, but I think we've got to really make sure that we do take care of ourselves and take care of the Earth so we can keep this beautiful place where the breathing is easy. So I'll finish there, and I just wanted to say thanks. Thanks obviously to the Royal Society for having me. Thanks everyone for coming, and thanks to my family who've been really supportive of all of this work. All of the SEDS Paleo group at Melbourne Uni, all my collaborators and students who I've abandoned now for a year of maternity leave. So yeah, thank you very much.
Thank you, Ashleigh. That was really a lot of information in all that, and I really had to concentrate hard. You'll be pleased to know we've had an overdose of geology this week at the Royal Society. We had on Tuesday afternoon we had the as I now call him President Emeritus Bill Birch mentioned. Leon Kostermans and Fons Vandenberg, Stories Beneath Our Feet, as their magnum opus, and this wonderful collection of information and stories of Southeastern Australia. But this has taken us back a long, long way before that, and it's one I really appreciate how you brought it back to, well, in fact, the box of marbles on the right-hand side of the last slide, and all the other stuff that's out there and what that might mean for us. So it's been a delight to hear you speak. There'll be some questions, I'm sure, from our audience, and some from online, doubtless, at some stage, Mike. What's next?
What's next? There's so much to do. I've got to write up every single other one of those reef complexes that we saw.
Okay. And find new ones.
And find new ones, exactly. Yep,
Yeah.
Exactly. Yep,
Okay.
Hopefully.
All righty. Is there a question from someone here? Yeah. Yes, Nikki.
That was fascinating. Thank you very much.
That's good.
Yeah. Those very early reefs, the Archaean with the crystal fans, what are they made of?
The crystal fans are made of a number of different minerals. One of them is called herringbone calcite, which is this weird type of calcite, calcium carbonate that has these kind of weird extinction patterns in it. But yeah, essentially calcium carbonate, and you get aragonite as well, which is another form of it. Yeah, and they make up these, you know, meter thick crusts of crystals that just grow directly off the seafloor.
Just different crystal structures.
Yeah, basically they're all little fans that you see radiating out from a point.
Huh.
So it would have been, I mean, pretty spiky, horrible place to walk around, I guess, but beautiful.
Pretty attractive.
Yeah.
Now there was a question. No, there's one there, and then Bill. Oh, sorry, at the back.
Hi.
It's good.
Hi. So I'm just curious. You're talking about the land. You said it was the land plants that contributed to the oxygen explosion. Obviously, nowadays phytoplankton is a huge contributor. I guess sort of I have a two-part question. Is it more about the fact that the land plants were sort of locking away those redox chemicals? And second of all, was phytoplankton a thing? Do we just not know because obviously they don't preserve very well?
Yeah.
So yeah, those are my sort of two questions.
Yeah, those are good questions. So yeah, so basically phytoplankton and photosynthetic bacteria and stuff that lives in the surface ocean do play a really big role in oxygen. And so it was those guys, was these sort of bacteria originally that oxygenated the atmosphere in that first big step. And they still contribute a lot today. And since the evolution of algae, there's been a lot more of these creatures that also produce oxygen. But I think that actually plants play a much bigger role than previously appreciated. I think there's recent papers that actually look at the actual numbers behind this, and I'm not exactly sure on the numbers myself, but yeah, from this work and from other people's work that they've done modeling this system, they've found that, yeah, it seems that plants really play the biggest role. And part of that, as you said, was because they form that organic matter really strongly. And when you bury that and you wash it into the ocean, that creates a bloom of phytoplankton, for example, and they produce oxygen, they die, and they all fall to the bottom of the ocean. And so it's that process that ends up adding oxygen to the atmosphere.
All right. You were saying that for a long time, the oceans were oxygenated on the surface layer, but anoxic below, whereas now it's oxygenated throughout. So what caused this change? For so long, it was only at the top, and now suddenly it's throughout the depth.
Yeah, that's a good question. So I guess in the early Earth, everything was reducing. The oceans were essentially in contact with the rocks, and the rocks were reducing. And so the oceans were just devoid of oxygen all the way through. But when you start to produce in the surface ocean with these little oases where the bacteria are living, they produce oxygen via photosynthesis, and that oxygen accumulates in the atmosphere, and then it can gas exchange basically with the surface of the ocean. And so the top bit of the ocean is oxic because the atmosphere has oxygen in it. But it doesn't really, you can wash it in with wave action and stuff like that, but it doesn't really, there's not really enough of it, I guess, to get all the way into the deep ocean because there's just not enough oxygen in the atmosphere. So it's only when you have abundant oxygen in the atmosphere that you can really start to pump it into the deep ocean. Oh, actually, I feel like I should know that, and it's in one of my slides that I use for teaching, but I can't remember it.
So I should repeat the question for those watching at home. So the oxygen levels now are also expected to be higher at the top of the ocean than throughout.
I'd have to get back to you on that. I definitely should know that. But essentially, it's all oxygenated in the modern ocean. It's all oxic. The only parts that are anoxic is where you get really high productivity and you deplete the oxygen, these oxygen minimum zones.
Bill.
Thanks very much. Firstly, I'm reluctant to criticise the president, but you can't have an overdose of geology. Great talk, Ashleigh, tremendous, really great. I want to go back to the first question that Nick asked, which was what was the mineral in the crystals you talked about, and you showed that amazing zonation pattern on the front cover of Geology. I mean, I can see why that got there. Is the variation, the zonation, just more than calcium, magnesium, or are there other elements, iron, manganese, those sorts of things? And if there are, how do you relate that back to the composition of the seawater at the time?
Yeah, that's a really good question. So I'll just find that slide. So the picture on the left there is the one. This is cathode luminescence image. So actually the cements themselves start around about the edge of the orange boundary and go all the way into this cavity. And the zonation is caused in carbonates is caused by iron and manganese, the amount of iron and manganese in the lattice of the crystal. And so here, these ones are actually from the near shore, from that tidal flat area. And usually, so if they're black, it means they've got no iron and no manganese. So it's oxygenated, basically. There's no iron and manganese in the seawater. But when you drop a little bit lower in terms of redox, you start to get manganese, and that gives you the bright zonation. So that you can really nicely see, in fact, without doing all the fancy chemistry, you can even just see it in the crystals themselves. So these ones probably are showing mostly oxygenated seawater conditions at that depth. Yep.
I agree with you, Bill.
Yes, no, I'm fascinated by this, but the story I heard about was that the oxygenation of the ocean led to the precipitation of iron as iron oxide, which led to all of these things like the Hammersley iron deposits and so on.
Yep.
And that these iron bands in rocks have a distribution across the Proterozoic that is quite steady, so that there's an idea of a progressive oxygenation and flocculation of iron to the seabed over time. Does your work suggest that
that those things actually stop at the times when your oxygenation levels go up? And I mean, how does that relate to the stories you've been telling us about oxygenation?
Yeah, that's a really good point. So the banded iron formations, the ones we see in the Hammersley where we get all that iron ore, they form around about the Paleoproterozoic here. So they go to up until about 1.8 billion, I think. So they start in the Archean and they go all the way through until in the Paleoproterozoic. So they're kind of, I guess I've simplified the oxygen history slightly here. This is in this traditional model, there's sort of this two-step thing, but actually one way to accumulate oxygen in the atmosphere is to pump it in there by organisms, photosynthesizing, but you've still got to remove all of the reductants to be able to keep it up there, to keep it in the oceans, for example. You've got to remove all the things that are going to reduce it and take it away. So that big pulse of iron formations that we see in the Paleoproterozoic is probably that removal of the iron from the oceans for the first time. And there's a big spike of iron formations just after that great oxidation event. So that's essentially the atmosphere is trying to accumulate oxygen. The oceans are trying to accumulate oxygen, but they can't because there's so much iron. And every time they add a bit of oxygen, it forms an iron oxide. It comes out. And so that sort of stops. You do get little tiny iron formations through the rest of the Proterozoic, but really these big ones only exist just after this first big event.
So what happens at the end of that, of the iron formation process, before your second jump?
Yep.
Why is the oxygen not going up then if your iron has been exhausted?
Yeah, so the iron perhaps has been exhausted by then, or is still, perhaps it's still in seawater. We see, the reefs are right here, and the seawater we saw was full of iron. So there's still a lot of reductants around, basically. And the evidence for the atmospheric oxygenation comes from around 800 million years ago. That comes from chromium isotopes.
Why don't you see further iron bands right up into the Sturtian and Marinaran?
Yeah, well, you do get iron in the Sturtian. Yep. So this earlier Sturtian glaciation is the kind of reappearance of iron formations in the record, and they're only associated with glaciation. So they're basically during this big ice age, you see this return to iron formations. But that's the only real blip of iron that you get in the record. And so both times you get iron formations are related to both oxygenation event, the kind of the titration of the iron out of the oceans. But you've got to titrate a whole bunch of other stuff too. And even in the atmosphere, even in hydrogen, you have to remove that. So there's a lot of stuff you got to get rid of on your way to pave this nice oxygenated world.
Just as a comment about the deep ocean oxygen, nowadays the cold water from Antarctica takes down oxygen into much lower layers, and so layers quite deep in the ocean have high oxygen.
Yeah. Yep. And that's been suggested actually with these ice ages too, that the cold water is allowed to retain a lot more oxygen because it's cold.
Question from online, Ash.
Just a couple of quick ones from Craig Bishop watching at home. Thank you for the talk. I'll pass that on. So he wants to know, where do flowering plants sit, I guess, along this timeline?
Oh, angiosperms. Now this is testing me. Anne-Marie? Later, basically later.
Thanks, Craig, for your question. Just to jump in, the oldest record of flowering plants is in the Mesozoic. So this is quite a bit younger than the Cambrian and Devonian. It's one of the oldest flowering plants was originally discovered here in Victoria from 125 million years ago, and this has been superseded by some that are well dated from Spain at the earliest of the Cretaceous, and there's contention about whether some from China are Jurassic in age. Thank you.
Yeah, thanks, Emery.
Great. Okay, we've got one up here, Richard.
Did you get another one, Scott?
Thank you very much for a really engaging and exciting paper. I would like to ask you a question, not specifically about your hypothesis, but more about the body of knowledge You mentioned that cool dude, Reg Sprigg, who was actually a student of Sir Douglas Mawson's, who was a colleague of Dr. Philip Law, who benefacted this prize. But having worked in Adelaide and also the Mawson Institute for Antarctic Research, I'm very aware of that history of philosophy and history of science linkage. But for you, coming across Reg Sprigg's work and the story of the Ediacaran fossils is a very strong story within scientific kind of geological narrative. But I was just wondering your linkage of multiple aspects of which the Ediacaran fossils is only one element. Did you reflect on how Reg Sprigg got to that point, but obviously not connecting the dots? Because I see your papers very much linking all those elements together that help us understand a holistic view of the evolution rather than a singular event, which I suspect is what the Ediacaran fossils represents.
Yeah, that's right. Yeah, that's a great question. So, of course, all science is built upon the science that comes before, and Mawson and Reg Sprigg actually did a lot of the initial work in the Flinders Ranges. And it turns out when you go back to their original papers from the 40s and earlier, it turns out they're usually right. Like, people have come and said things since then, but if you go back to their Mawson's original work, for example, on the glaciations, it turns out even without, he just wandered out there, no cars, nothing, none of this fuss, and they got it right. So it's amazing that, and sort of the only way that we're able to link it together is to build on that really rich history. And that place, the Flinders Ranges, is such an amazing place for geology. It's just this fundamentally beautifully preserved part of Australia that, you can see why people went there and just fell in love with it, basically. And the Ediacaran fauna, when Reg Sprigg discovered them, I think no one believed him for ages no one believed him that they were pre-Cambrian. And he really fought for it. And, it's just that history of finding weird things and fighting for them is also sort of what we've done with these reefs and trying to figure out what those little organisms were in the bottom part of the reef. There's something weird. And hopefully by the time 50 years down the track or 100 years down the track, someone will be looking back and saying like, oh, good on them for documenting them.
That's awesome. I do have a couple of questions. The main thing is like understanding that the snowball Earth phenomenon seemed to occur after a massive spike in oxygen levels, which of course, I guess, brought down the greenhouse effect from the other atmospheric chemicals that were in the atmosphere at the time, presumably from land plants oxygenating. Yeah, not trees, obviously, by that stage, but land plants obviously started to kick in, but animals were kicking in then too. So I'm very interested in understanding the correlation of the carbon cycle with the spike in oxygen rates to understand how the carbon cycle was starting to kick in and that incredible relationship between animals and plants to sustain the oxygen carbon levels. Yep. In the oceans, in the atmosphere. Could you reflect on how much carbon is actually sort of tracked through these same periods and your ability to do so? Yeah, definitely. So the amount of carbon dioxide in the atmosphere, I guess in geological time is generally fairly uncertain, but probably in this early part of Earth's history, and particularly really early on, it was probably very, very high. Thousands, tens of thousands, hundreds of thousands of ppm, particularly in the early Archean when the sun was really faint. You needed a lot of greenhouse gases like methane and carbon dioxide to get it going. But I guess in the Sturtian and Marinoan, these two big glaciation events that we see in the Neoproterozoic, they are thought to be a fundamental disruption to this carbon cycle. And I guess the carbon cycle we learn, for example, that's taught in school, focuses on the ocean and the trees and the atmosphere, but it doesn't focus on the long-term carbon cycle. And really, the long-term carbon cycle on Earth is what controls the climate. And it's what beautifully has made Earth habitable through its long history. There's always these feedbacks, these negative feedbacks to kind of keep it in check. And the snowball Earth was a representation of one of these feedbacks. So there was ice that formed, and it formed at really low latitudes on the equator. Then basically the reflectivity took off and it cooled even further.
And what happened under this theory, Paul Hoffman's theory, you then seal off the oceans. So you can no longer exchange your atmosphere gases, and you build up, but you're still pumping out CO2, carbon dioxide, from volcanoes. And eventually you fill the air with so much carbon dioxide that it just catastrophically melts the ice. And that level apparently is thought to be about 120,000 ppm carbon dioxide. So we're at 400. It's 120,000 ppm.
But still, we're also talking about hothouse Earth, but never mind.
Yeah.
Let's just park that for the minute.
Yeah. So yeah, but definitely, you know, the evolution of animals, the evolution of plants, all of these climate conditions, they play a huge role in carbon cycling.
I do have one last
more
question.
question, Mike.
That was an awesome answer, and that filled in so much for me. The one is on your astrobiology work. You know, when you were at Yale, you were working in an astrobiology unit as well, which fascinates me. You know, so they're starting to call it planetary sciences now rather than simply geology as well, which is terrific. What we learned from Leon Kosterman's launch the other day, which is very much a beginner's guide to geology, but a fantastically elaborate one, was how much of the Earth, as in the entire planet, is made up of oxygen. So if you're looking at that pre-Cambrian life, which obviously was existing with very low levels or no oxygen whatsoever, if we're going to look for other life elsewhere, we know, or from your work basically, and those of your colleagues, that life can exist without those sort of oxygen levels. What else should we be looking for? What's that telling us about what's going to give us a sign of life out there in the universe?
That's a really good point, and I'm sure many qualified people have talked about this more so than me. By the idea of what they call atmospheric biosignature, or a signal of life that you could see in the atmosphere, is disequilibrium. So things that should not be together. You need something that is pumping in methane, for example, or oxygen into the atmosphere. That's a sign of life. So it doesn't have to be methane and oxygen. It just has to be a series of gases that shouldn't be together. They should sort of peter out and form, you know, one type of atmosphere. So any sort of disequilibrium, I reckon, is something to look for.
I think Ashleigh's done a great job. I think we might call it to a conclusion there. Ashleigh, congratulations again on being the winner of the 2022 Philip Law Postdoctoral Award. We're delighted to have you present tonight. I have a little presentation to make to you. It's really so that you can put that in the office or somewhere so that we can, Mike's going to take a photograph of us. Come over and stand in front of the what's it? Here we go.
Pretend you're happy. That's good. They're good.
It just means you'll be in our magazine as well. Thank you for being with us. And I think we retiring downstairs for something or not.
Yes, we are.
Yeah.
We may retire downstairs for something.
Yeah, there's something downstairs. I don't know what it is. I know your young family's looking forward to catching up with you as well. So thank you very much for being with us.
Alrighty.
And that concludes this this evening. You've come downstairs for a little something, as Rob has invited. And to those on Zoom and YouTube, thanks for joining us. We'll leave it